Welcome to Breadboarding. This is video 31 in the Breadboard 8088 PC series, where we're looking at building out PC compatibility, and this is part 9. We'll be testing the interrupts and the direct memory access controller. In previous videos we've added the interrupt controller, timer, DMA controller and floppy disk controller, but we haven't really been able to test all of these thoroughly so far. And really, when we try and actually boot off floppy disk, then this is the first time we're really going to be bringing all of these parts of the system together into one go. Now what I'm going to do is to try and boot off the floppy disk first of all with the system as it is at the moment, and needless to say it doesn't quite work at the moment, and then I'll take you through some of the steps I've been looking at to try and work my way through the issues. Okay, so I've just started an Nanocomp. We just need to download the BIOS and load the BIOS so we can get it ready for running. So I'm just going to change the Nanocomp to load into the 6000 segment and load. So that's where we've put our BIOS. I'll just speed this up because it'll take about 30 seconds for the BIOS to download. So that's finished. We also just need to get the logic analyzer for the power on self-test lined up. So that is triggered on the post clock, power on self-test clock. So we'll just get that ready, and then we'll go to the video capture card and we'll start up the system. Okay, so ready to start. So press final 0. So we get the power on message, then we've got the testing RAM and it's trying to boot now, and there will be drive access sound there. If we press enter, then we'll get another boot failure. So we need to get to the bottom of what's going on and why the booting is failing. Let's take a look at the logic analyzer output for the power on self-test port. So you can see here that we've got power on self-test going from 0 up to about 12 seconds. So this is the gap between the retry for the boot. And down the right hand side here, it's a little small, but you should be able to see it hopefully. We've got the power on self-test codes that go initially from 01 up to about 43. And then the 0 power on self-test code means trying to boot. And what I have done is I've added some extra messages, extra power on self-test messages to the boot code in the floppy disk stuff. So anything beginning with a D basically means it's floppy disk related, and sometimes I've also got some of the values returned from the floppy disk drive. So it's definitely accessing the floppy disk drive, and in fact it gets all the way down to the D9 stage. The DAs is where it's waiting for interrupts, and then it actually retries a couple of times, and the DF is the failure. So you can see here that it is definitely accessing the floppy disk drive. It's trying a number of times, and then ultimately it fails, and the DF and finally the CF means it's failed the whole thing. So there's some problems going on here, so you need to look into what's going on here. So if we take a look at seeing which systems we actually need to be working for this all to be able to boot. So this is the diagram from the original technical reference guide, and this is what we were using in earlier videos to look at what all the different systems we need to worry about are. And we can see here that we have the interrupt controller. So the things in purple are the things we need to worry about testing here for the floppy disk to work. The programmable interval timer, the DMA controller, the DMA address latch and the DMA page register, and then there's also potentially DMA data buffers, which I'll talk about in a few minutes. And basically all these things need to be working for the floppy disk to be able to read data off of the disk and load into memory. So as well as testing these components, there are some other issues that I did come across, some fairly minor. So the green run LED that I had to show me when the board is out of reset and it should be running was not working. So it should be showing green whilst running. It goes off during reset. So I've replaced that LED. Also, whilst I was testing out the floppy disk controller and the other chips, the PS2 keyboard became unstable at power on self-test. So we were getting various error codes and things appearing in the post logs. And it turned out after several days of going around in circles that in fact the dual mouse and keyboard PS2 connector that I made, there was a broken copper track So one of the copper tracks on the strip board had lifted off. It's quite old. The strip board I'm using is actually fairly old, probably about 40 years old. So I suspect I might need to replace that for future projects. And basically the copper track had lifted off the board and broken. And I thought it was the connector for a while, but I later found out. So I've fixed that. And also at the same time, I also found that the actual keyboard controller chip I was using at the time, that the P27, so port 2 pin 7 output, which is the keyboard data, wasn't actually producing any output for some reason. So I swapped that around with the chip that I've got from the 6809 project I did, and that was all working. So the keyboard caused probably about half a week to a week's worth of delay initially. Whilst I was doing that, I was also finding that the LED display on the Nanocomp monitor, that when I powered it on, I had to press reset probably 2 or 3 times before I'd get the Nanocomp sort of startup message on the display. And I looked into it, I found out that since we've added the various timers and interrupts and things, and that was interfering with the monitor startup. So what the version 4 of the monitor now does, which is what I've updated it to, then it disables the interrupts, masks the interrupts for the 2 programmable interrupt controllers. I was also getting the register display appearing a lot under certain circumstances, and I realized that when I originally was setting up the monitor, I defaulted a lot of the interrupt vectors to go to the register display. And so what I've done now is I've added some more sensible interrupt vectors, and I've also added the dummy end of interrupt and IRET handlers for all of the hardware interrupts. So basically, if any of the hardware interrupts occur, then the monitor now handles that properly. It wasn't a problem when we first added the monitor because there's no interrupt controllers and no timers, but since we've actually got those, then that's actually made things a little more complicated. And I've also added, this is unrelated to these issues, I've added some far wrappers, so a cross segment boundary, so that we can call the various monitor, keyboard and display routines from other data segments where it was a problem I had. So those number of issues that I fixed there. So let's take a look at what tests we need to do for the programmable interval timer and the interrupt controller. So the programmable interval timer is actually doing the power up sound, so the diddly-dip sort of sound that you hear in the first couple of seconds of power on is actually using the programmable interval timer. And there's also system timer on interrupt 0 that uses this, so we'll talk about that just down here below. Now the programmable interrupt controllers, there's 2 of these that we've got in the system, which is closest to the PCAT and upwards design rather than the original XT. And IRQ0 is the system timer, which actually fires every 55 milliseconds or so, which gives a clock of about 18.2 hertz. Now after any interrupt fires, then the CPU will signal the interrupt controller with 2 int-A signals, and what the interrupt controller should then do is put the interrupt number on the data bus. Now the interrupt number will actually be the vector which the CPU needs to use to find which routine it needs to call to service the interrupt. PIC 1, so the interrupt controller 1, has an interrupt vector offset of 0.8, and these are initialized as part of the BIOS power on, and I now have actually put these into version 4 of the Nanocomp monitor as well, so these will be correct when the Nanocomp powers up. And PIC 2 has an offset of 7.0, so this basically means that the IRQ0 on PIC 1 should have 0.8 appear on the data bus on the second int-A, and if we had the first interrupt on PIC 2, then that would be 7.0 we'd expect to see. And then the CPU then uses that to calculate the interrupt offset it needs to call the appropriate interrupt handling routine. So we should see IRQ0 write 0.8 to the data bus when we get the second int-A. And then after that, what the interrupt routine needs to do is send an end of interrupt EOI to the PIC, and you'll see that the code it does for that is 20 hexadecimal. That tells the PIC that the interrupt handler code has finished. So these are all the things that need to be working for the timer and the interrupt controllers for us to be sure that that's all working. So we'll take a look at the logic analyzer output from that. I've reconfigured the post monitoring configuration here, so the data bus here is not, it's on the other side of the post buffer, so it's actually the data bus. We've still got the post clock, then we've got interrupt 0 or the output 0 over the timer, then we've got the CPU interrupt, the interrupt acknowledge, and then we've got the chip select for the interrupt controller and the timer. So I'm just going to boot system up and we'll record the first couple of seconds of what's going on here. So let's take a look at the logic analyzer output. So this is the boot up from Power on Self-Test, and we can see that where we have the post clock here, if we drill down into here, we should be able to see what the post codes which are being logged. So we can see here that that's 01, a little bit further on 02. Now if we look at the codes, we can see that in fact initialize the timer is 06, initialize the interrupt controller is 07, and enable interrupts is in fact 09. So when we have a look at some of the other codes a bit later, then that's how we can tell what's going on. So what we've got here then is we've got our post codes going here from time to time. We've got the interrupt 0, which is the output 0 of the timer. So down the bottom here we can see that we've got some configuration of the timer early on, and shortly after that we can see that this IRQ0 starts. And if we look at the period, so if you look at the top right hand side over there, then we can see that that's about 55 milliseconds, about 18.19 hertz. So that's the basic output of the system timer. The timer signals here I think are the power on beep, so the little diddle then is done by this, so this will be the 4 notes that are actually being used for that. And we can see here that although the timer produces a signal here, we don't actually start to get any interrupts being generated until a bit later on. I think if we go into here we'll see that the interrupt controller gets initialized around here. So if we just see what these post codes are, so yes, we got 07, which is initialize the interrupt controller. Then I think 08, that will be something to do with the keyboard. And then what we will probably then find is that the CPU won't actually start acknowledging any of the interrupts until the interrupts are actually enabled. And we should see that the Power on Self-Test code here, I think the first one here should be 09. So yeah, so we got 09 up there. So that's where we're enabling interrupts. So only at that point in time, when an interrupt is actually registered, will the CPU start to do anything about it. But obviously during the code then there's clearing interrupts and setting interrupts. It enables and disables the handling of interrupts. So if we have a look at one of the first interrupt acknowledges here, so we can see here that the IRQ0 timer output 0 is going high here. We're actually getting a fairly short interrupt here. Up to this point in time, obviously the timer output and the interrupt were basically in step, and the reason for this is that because the processor and the interrupt controller are not doing anything to clear the interrupt, then it will look like this. But as soon as the interrupts over here start to get a lot skinnier, then this actually means that the interrupt is being handled. So if we look at this rising edge here, this causes the interrupt controller to message the CPU using the interrupt lines. And then we can see here that in fact we get 2 int-a signals coming down here. And on the second of those signals, what we should see is this is the CPU asking the interrupt controller, can you tell me which of the interrupts caused this? And we can see here the 08 up here. So that appears to be working. So it looks like the timers and the interrupt controllers are all working okay. And this is important because when we come to the floppy disk controller, the floppy disk controller uses interrupt 6, and so we need to make sure that's all working as well. When we look at the interrupts here, when we see that the interrupts narrow here, it's because we're then actually getting the CPU is then running the code to handle the interrupt. And that code also will then, if we go into this chip select here, what we'll also see is once the interrupt routine is finished, you'll see up here that the interrupt controller then actually has 20 written to it, and this is the end of interrupt. So this basically completes the whole sequence. So what we can tell here is from the interrupt being raised to the end of interrupt being signaled to the interrupt controller, we can see that period there is 91 microseconds. So the time taken to process the routine timer message is about 91 microseconds. So there's quite a few clock cycles needed to do that. And for this reason, obviously, if you have lots of interrupts going on, and the issue I had with the monitor was that some of the interrupts were going on and they were actually causing complications because there weren't the appropriate interrupt vectors, so it's just going off to random places. So that's the reason why I had to fix the monitor. But what we can see here is that the timer and the interrupt controllers seem to be working correctly. So now let's take a look at some of the other issues I had to address. So as I was testing the floppy disk controller and doing other tests, I did find there was some instability when I had the floppy disk controller, interrupt controller, DMA controller cables all connected. And I went through and I counted up on the schematic. There's more than 20 chips now on the data bus. Now, theoretically, the 74ALS245 that we're using is capable of driving up to 40 loads, although I guess some of the chips might actually not be an ALS load, they might be an LS load, so that might be a little bit lower. So I was getting checksum errors when downloading the BIOS, and also occasionally would also get memory failures when the BIOS was testing the memory on boot up. So what I've done, I've added an extra 74ALS245 bidirectional buffer to piggyback the current buffer. So that basically just sits over the top of it on a little adapter I made that I'll show you in a minute. I also added some 10k pull-up resistors at the end of the data bus, so I was hoping that that would also help to reduce perhaps reflections and things. I do know that trying to do this number of chips on breadboards and DuPont cables is probably pushing the electrical characteristics somewhat. And I also found that there was an intermittent fault on one of the connector cables on the top bit D7 line that caused some problems. I tested the end-to-end output from the data buffer at the CPU all the way to the end using the continuity tester and found that fairly quickly. And then finally I managed to miss out some pull-up resistors missing for a number of the signals here, which I'll go in and explain on the diagrams now. So these original diagrams from the PCXT that we were looking at, and if you see here on the interrupt acknowledge coming out of the interrupt controller and goes into the bus controller over here, the 8288, you can see here that there is actually a pull-up resistor here, and there's also pull-up resistors for the IO read, IO write, memory read, memory write. Now, under normal circumstances this doesn't really matter too much, but when you are switching between DMA and CPU, then there could be periods of time when these signals could go low and I guess could cause some random writing to memory, which would probably cause a problem. And also when I was actually trying to diagnose some of the problems here, I realized that without that pull-up resistor on the EOP output, which is open collector, then you won't actually see any signal on this. So again, we've added those as well. So if now just take a look at the board and I'll just show you what I did with the piggyback buffer connector. So it's quite messy at the moment because we've got a lot of logic analyzer cables going across the place. So once I've got rid of all of those, then I'll tidy up the board a little bit. Now if we look over on the right hand side down here, just check the power is off. Yeah, the power's off. So this is where the output from the CPU data buffer is, and all I've done is I created a little piggyback. So I managed to, from the local supplier I use, Bitsbox, they had these quite nice little riser things here which you could actually make a chip holder that goes over the outside of the existing chip and just allows us to piggyback another chip of the same type over it. So basically I just plug that in over the existing 245 chip, just make sure I don't get the pins wrong, and that seems to have actually stabilized things. So we're up to about 19 minutes now, so I'm going to break the video and we'll look at doing the DMA controller in the next video. So we've managed to prove that the interrupt controller and timer are all working. The floppy disk controller is causing the floppy disk to do some activity and we're getting quite a bit of data back from it, but I suspect that it's the DMA controller bit where the data is actually taken from floppy disk controller and written into RAM, which is causing the problem. So if you don't want to miss out on future videos, please hit subscribe, and if you could hit like, it just helps to make the videos accessible to a wider number of people. Thanks for watching.